Hello and welcome to creating a compiler from scratch, recreationally. That's right, we are recreationally programming here. I have scaffolded out a little project here that I can briefly explain and go over the goals of this compiler here. It's going to be an MIT licensed project. I'll have the link to this source code in the description so you can come check it out whenever you want. And I've briefly put together a little README on some goals and a high level of what I want to do. Let's open up a preview panel. So if I can spell, preview to the side here. So we're going to be implementing a compiler for the Laie programming language in C with an asterisk, because one of the goals of Laie is to interop directly with C as like a native feature. It's one of its primary goals is just working with existing C code, writing C and Laie code in the same project. So we're also going to attempt to make a C compiler. How far we're going to get and how useful it's going to be will be interesting to figure out along the way. The high-level goal is the Laie compiler should be self-hosted in C exclusively. We should be able to write a compiler that can compile itself in C that also happens to support the Laie programming language, and we can use those features to build out our own project structure, include system for Laie, and whatever build tools we want and stuff. And we'll get there when we get there. Maybe that doesn't make sense. We have very minimal dependencies. By minimal, I mean we depend on, you need to have CMake to build the thing, because I just want to not have to think about building it, and that's it. The interesting part in self-hosting here is that means we also have to limit our use of the standard library to a point where I can use my own headers. We don't want to try to make the leap to parsing the C library headers given to us by the system. So I've also tested out that I can just create my own standard IO header here, and well, beautiful, now I have my own header that is much easier to parse. So we're going to be limiting ourselves to a subset of the C standard library for a little while, just to make sure that we can lex and parse enough to also self-host the lexing and parsing of the compiler. Eventually we'll be able to parse better files, and we might not have to rely on this anymore, and we can remove our makeshift library headers, but temporarily we're going to be a little bit limited here. Again, the build instructions are very simple. Just use CMake to build it. I will run through this here just to show you what's going on. Let me actually remove my other build directory. I've got a little build script that I use for CMake projects, so you won't have that, don't worry. So if we follow the instructions over here, we want to CMake B build. I'll just copy pasta right there. And it's going to do a configure process for us. I'm in the wrong... We want to be over here. Wrong repository. Doing it live. That is right. You will do that, and then you'll do CMake build. I need my generator. So anyway, pretend that works. My build script has my makefile generator set up. I can't use MSVC on this system. It's borked. I need to fix it. We are using Clang with MinGW on my end, and I'm also going to be testing this in a WSL instance, which is running Ubuntu. So we're going to be making sure this works on MinGW in Windows as well as in a Linux distribution. And then we have a high-level goal of, if we can get it to compile in MSVC as well, we will. I'm not worrying about it from the start, though. I don't want to do that. So we can start over here with our project template. We are going to have a library that has all of our actual library sources and whatnot for writing this compiler, so that we can still link other tools to it statically or dynamically in the future. We don't want it to all just be an executable. We want it to kind of be designed around an API, because we might want to use it for other tools later. But the main source file here will be the driver, which actually has our usage and delegates our command line inputs into the library. I'm also going to be experimenting a bit with the design of the data structures in this compiler. I've written a lot of compilers. None of them have ever been fully featured compilers, but I've written a lot of compilers. And I'm getting a little tired of the tedium of a giant AST, abstract syntax tree, for our parse tree. So I am considering a post order array for our parse tree if I can make that work. And I don't really know how to explain that because I'm still learning about how that data structure would work in the first place. But let me open up a new buffer here and we can make it bigger. So let's say we have int a equals 10 in probably C, but this is also going to be valid LaYeA code, so it can be either one. The idea of an abstract syntax tree is simply we have, okay, a variable declaration. And we need to know the type, the name, and optionally the initializer. So we can have over here a type int, and that's the type of our variable declaration. But then we can also have the name ref, the name that the variable declaration is declaring. And then we can also have a an initializer here, which would be like, I don't know, literal int with a value of 10. So that would be like our simple parse tree for just this statement here, right? We have the variable declaration and all of the subcomponents of the variable declaration in a tree. So you traverse it, variable declaration, okay, I need to know the type. Then we go back up and say, okay, well now I need to know the name. And then back up, and now I need to know the value that's assigned to it, which could be non-existent. But I've been learning a little bit more about alternate data structures for this, and I'm thinking we could maybe use this same thing as a sentinel to say, hey, we are starting a variable declaration. And then the first thing we have is a type. And if it's a single terminal, we don't have to have a sentinel for it here, right? We could just say type int, and it knows that it's its own sentinel and terminal. So we just have var_decl, cool. The next thing is a type. We immediately resolve the type. There's nothing else to see because it's just an int. Then we know that we're looking for a name. So a name ref is also a terminal. It is just one token. So cool. The variable declaration knows it needs at least a type and a name to declare something. And then the semicolon would be our end var_decl, which is great. So if we see an end var_decl here without an initializer, then it's just a declaration with no initializer. But if we haven't seen an end var_decl terminator yet, we can look for any expression in here to be the assignment value. And so we can use these like delimiting nodes here to start and end in like a stack machine, kind of not like a stack machine, but it's definitely stack based, right? You can push and pop things off of the stack and resolve them as necessary in whatever order. And you can just iterate through them, 0, 1, 2, 3, 4, 5, they're adjacent. So all of your relationships are adjacency based instead of pointer through pointer through pointer through children into the heap. So I want to try something like this in the AST as well. So we may have some fun learning about new data structures when we get there. If you've never seen a compiler written before, I will try to be a little bit explanatory and not assume too much prerequisite knowledge, but I'm not going to be teaching how to write compilers and what everything is, unless somebody asks in the comments or I start going on a live stream to talk about it or something. If we're doing pre-recorded episodes, the default is just going to be I'm going to talk about what I'm doing. And if there's enough questions, I can address them in another video or, like I said, in a live stream or something. I am antsy to get started on something, though. So, again, we're trying to keep this simple. I'm not going to do a whole bunch of scaffolding of here's every type I'm ever going to want. Here's a whole wrapper library around the standard library. Normally, I would do that for a project, so you've got access to all kinds of nice APIs for the base layer of like, okay, here's a string type, here's my signed integer types that you get from the int types, whatever. I'm just going to assume we don't care, and we're going to move on. So the first thing we're going to want to do, I have a goal here, is we want to start lexing C, ignoring the C preprocessor for now. I have started a project where I was writing a preprocessor and never got far enough to test it, so I might use some prerequisite knowledge from starting that to influence the lexer's design. And for those that don't know, a lexer is going to turn textual representation of a program into more manageable pieces, like the keyword int. We don't care that it's int, we just want to know about the keyword int. So we can read through and say, hey, I know what this is. We're just going to turn all of these into a single keyword token that we can reason about better at a higher level. So that's goal one, is a simple C lexer, which should not be hard. C is pretty trivial to lex. Parsing is a little bit harder because you have to have some state involved, but we'll get there when we get there. I want to start without the preprocessor with a little bit of prerequisite knowledge, and then we want to move on to, okay, let's try a subset of the the preprocessor. What I think will be a requirement pretty early on if we want to start lexing ourself is we need if def, we need define, and we need include. We might need a couple of other things, but if we look over here, we're including our standard library headers. We don't really want to be copy-pasting declarations everywhere, so we're going to want to get include working pretty soon. That's probably going to be the hardest one to do, correctly at least. We could probably get an incorrect implementation working, but correctness will take a sec. And then in that file, we have if and def and the endif, and define to give us our include guards. That is the bare minimum to get us working with the preprocessor. So that will be our first target for goal number 2. Can we lex that kind of stuff? Ideally, we don't introduce anything else fancy in the meantime so that that truly can lex all of our project source. If we need to use some other preprocessor stuff because C sometimes needs it because C, then we'll add that to our list of whatever our subset is, and we'll make note of it. We'll consider all of our C-lexing done when we can, in fact, successfully lex the project source. Again, get all of the tokens out of every file in our project source. And then we'll start working on the actual Laye implementation. Laye, again, is my custom programming language that I've been designing and failing to implement for myriad reasons over the past decade, I'm not going to lie. But we're going to build Laye C from the ground up for fun, because it just sounds like a project I want to do. This, if I'm going to build Laye, this sounds like the way it should happen. I'm not going to rush the process. We're going to do it right, and we're going to do it completely from scratch because I like doing that. And then from there, you can read the README, or we'll go over the rest in future episodes, because lexing these files, while technically trivial, is still going to take us a couple episodes, probably, depending on how much I do off camera. We'll see audience response. If you guys want to see me do absolutely everything, then I will do absolutely everything. If you want to see me go over some stuff that I've done in the meantime and let me do stuff off camera, then I will. I would love to do things off camera. It might end up being that I record 5 episodes a day because I'm antsy to write code. Who knows? Let me know what you want to see, and we'll try to accommodate you. I'm going to end up filling out this README with more information later. Like, I don't do open source correctly very often, so I don't know what to put into contributing, but I will accept contributions. I just need to figure out what to put in here. Right. So without any further ado, let's start scaffolding a lexer, I guess. The lexer we're going to keep pretty trivial. So in Laye C, we need... I think we want new folders for Laye, the language we're going to have second, and C, so that we can keep our data structures just a little bit more separated. There's no namespacing in C, so we're still going to be using a lot of prefixing on our types and functions. So they're not really going to clash, but just for logical separation and ease of finding things, we're going to keep them in separate folders. So in C, let's just make a token.h. What we want here is all of our data structures related to tokenizing, lexing a C file. So if and def Laye token h. The include file path is usually what you use as an if and def, and we've got Laye C token. I don't know if you can see that on the screen. Maybe I make this slightly bigger for... I don't know. I don't know how it's going to look. We'll see. So set up our little include guard for our include path here. And I know we're going to want a type def for a struct called Laye C token, probably. I like being a little verbose, but we might want to remove the Laye C prefix. I don't know yet. Laye C token. We'll have a C token here. We're going to eventually want some token types as well, but for right now, we don't care. You know what? I might just want to have a token class or struct at the Laye C level that both C and Laye can use, because tokens aren't that complicated. The complication, I guess, comes because C's token is going to have preprocessor information in it, so maybe we don't really want them to overlap, just for, again, logical separation. So for right now, we'll be fine. we know a C token is going to have a type, which I'm just going to name int for now. Int kind, we're going to use the word kind, not type, because we want to talk about types separately later. So to avoid confusion, we need the concept of a location in the source. So that will be shared between Laia and C. So let's go ahead and come over here and just say, let's make a source.h, which is going to give us utility functions around using source text and files and stuff. So we want a ISE location. And just for everybody's reference, I am going to be forward declaring a bunch of things like structs just ahead of time to avoid any future potential order dependent shenanigans. So you're going to see a lot of type def struct something something, and then the struct declaration later. So I can put all of my struct type defs at the top, and then have pointers to things without having to forward declare or use the, I forget what this is called, the like explicit prefix on a type. Anyway, we're going to do it that way. That's what you're seeing. So we want a file ID, probably. We don't want to store an actual file in the location, so we could just say int file ID. And then we want the location, offset, and length, probably. We could do offset, like start and end offsets. I usually like offset length. It's a little bit, it doesn't really matter. So let's do a long man, offset and length. And that'll be our location. We can use the offset and length to compute where in the file we are, line and column, at a later date. But this is a simple enough location. I'm avoiding using any of the predefined, like if we were to include standard int.h and we get like int64t or something, I'm avoiding those just so I don't have to implement the header myself. Eventually these will probably be refactored. Maybe. I don't know. I could go ahead and type def them somewhere and then move them into the header later. Or I guess I could implement the, maybe that's something I do off camera, is implement some of those headers. Unless you guys want to see it. But for right now, I don't really care. We're going to take it slow and just go with the flow. So we have a location. Our token can now have a ISE location. And I don't think my Visual Studio Code setup is smart enough to know how to do that on its own. So we're going to include ISE source.h. Cool, so there's our ISE location. And that is the bare minimum for tokens. We will want some additional data here, but how we're going to store that data is up for interpretation at the moment. Like the obvious one is we can say long int value. And we can have a signed integer constant, basically, which can also apply to other things later, but for the moment, it'll just be integer constants. We could also go ahead and add a double for a real value. Real being, you know, ooh, why doesn't it like double? Okay, it does. Real just being the word for like any non-integer number, like in that format. Float is the specific implementation. We're going to use the word real when we're not talking about the implementation type. Probably. Sorry for the sniffles. As soon as I started recording, my food, nice warm bowl of ramen, hit me and started messing with my nose. So the real question, I guess, is going to be, how do we want to store our strings in the compiler as a whole, but at the very least in the token? The obvious thing to do for identifiers and keywords is not allocate any additional memory and just use pointers into the original source file. And for when we have to do string literals and stuff, we will have to build strings ourselves. We may have a wrapper type for that. We may do it manually in the Lexer. I don't know yet. But either way, we'll need some semblance of a card data, like a string value, and we could do like a usize. I'm going to just call it long as well for string length. And if we notice here, these two are the same type. just with different names. What we might end up doing is turning these into separate structs and putting them into a union. I am not super well aware of where the C standard draws the line for unnamed structs and unions. I use them all the time, but I don't think they were introduced until C11. So depending on how we go about parsing C, we might want to start with like a C99. Probably not going to do C89, honestly, but if we start with like a C99, then we might not be able to lex or parse anonymous structs and unions. So for right now, we're not going to care about the layout here, but we very well might want to, for space, that's not a huge issue on modern CPUs and stuff, modern computers as a whole, but we might want to make this smaller and use unions and stuff later. We'll figure it out. For right now, string value and string length will just be this, and we can wrap it up later. So there is most of what we need to start lexing C. Again, preprocessor shenanigans in the future, but for right now, that is fine. We also need the idea of how we're going to get files. For right now, I said, hey, we've got a file ID. And the idea here is we'll have some file store that we can request files from. Hey, get me this file if it exists, and if it doesn't, create it. And give me an ID that I can reference it by. So, do we want that to be a separate thing here? Maybe. Or do we want to go ahead and create a context for which all of our compiler can access everything? I think we just want to put it into a context. So if I go into LIAC, let's create a context.h. Then we can go over what a context is. Type def LIAC context needs a struct prefix LIAC context. So then struct LIAC context is going to have a couple of things here. We are going to have to implement our own dynamic arrays as well, and that's probably what we're going to end up using for storing things like source files or lists of tokens and whatnot. We need to be able to dynamically allocate some memory and push and pop things onto those lists. So in a perfect world, we'd have like a list type that would take in, here's our like string that we want to whatever, or our source file, or whatever, right? We don't have that right now. What I'm probably going to do is manually do it for a little while. So if we have the concept here of, let's call it a source buffer, we're going to have some buffer of text. We don't care where it came from. This is where we're going to put all of our source text information. So we need a car pointer source text. And we can make this a const car because we never really want to modify the source text once we've created it. If we want custom files, we'll want to generate the text ahead of time. Why doesn't it like that? C car isn't defined. Okay, well, it's just slow, that's why. And we could go ahead and also have, sorry, I was saying something. If we want to have custom files that we generate within the compiler, we can do that and then just, assign it to the const thing and never assign it again. So we don't care, once we've got a source buffer, we don't want it modified. Do we care about the source length? And we're already in a source buffer, so I'm just going to call it text and length. We can pre-compute the length just in case, but in most cases, we really just want this to be 0 terminated. So I don't think we care about the length. We're going to assume that this is, if I remove the brief, can I say null terminated string containing the source text for this buffer? That should still work in this IDE, yeah. Let's start documenting things. I'm bad about documenting as I write stuff. So, and we want a const car for the name of the buffer so that we can refer to things by name more easily. The name of this buffer. This could come from the file path used to create it, or how do I want to word the next half? Or arbitrary for compiler created files. Something like that. Cool. So there's our buffer. If I come up here, it already knows it. That's cool. So then we have a LIAC location. I'm really bad about writing good documentation, so forgive me if it takes a second to think here. We want a LIAC location. Well, let's come down here. We know we've got the ID of the file that this location references. Sure. And then we can like include other stuff about, let's say call, and we can call it LIAC context get source buffer of LIAC context, and we'll just call it int. Now let's see, this is where we want context and file ID to get the source buffer itself. Offset index into the source buffer's text. Does this actually render, or am I doing? Oh, interesting. That's a lot of backslashes. If I remove these, do we not get the backslashes anymore? I don't know how this renders stuff. That's fine. We're going to remove all of our backticks. Not backslashes, backticks. Offset into the LIAC source buffers. LIAC context and file ID. Cool. Where this location starts. The length of this location in bytes. Offset index in bytes. We're going to specify these things here. Then an ID less equal to 0 is not valid. That means that anytime we initialize an empty LIAC location, it points to an invalid thing. We're going to one index our file IDs, then a reference to a specific span of text in a LIAC source buffer. Cool. So now we know what these are. Now we can come back into our context and start doing some things with this. We're going to have a pointer to LIAC source buffers called sources, probably. And then we can have a long sources count. Again, we don't have dynamic arrays yet, so we're going to have to just deal. We're going to want to include LIAC source.h to get access to that. And let's go ahead and copy out the one function we did reference here. We referenced this. So we want a LIAC source buffer, this. And we can return value here because we're not intending to edit any of these ever. If we do, we don't want the changes to save, so we're going to return by value, not make us indirect through pointers if we can help it. It'd be really cool if we can keep this really small and make the copy trivial. So that will do something. Let's start documenting here. Maybe I write the docs offline. Tell me if you don't like me explaining things in the docs. Get the LIAC source buffer associated with the given file ID. And we're calling it a file ID. Maybe we call it a source ID because we're getting source buffers here. Let's call it a source ID. Let's go update some docs here. Source ID, the ID of the source buffer that this references. Cool, that should be better. If an invalid ID is given, an empty source buffer, an empty buffer is returned. And the problem with the text being a null pointer here is we can't zero initialize it. So we maybe do want to have the concept of well, again, if we're null terminating the string here and we don't care about having our own custom string type for now, then we should probably just be checking against null, which is fine. Sure. So that gets us our source buffer. We'll also need a way to create a source buffer as well as a context, actually. So let's do some of that. Let's make a context. And again, the context is for storing global state, quote-unquote global state, because we might have multiple different compilation things happening at once in the future. We don't know. So rather than global variables, we're going to pass around this context, and that'll be our surrogate for global variables for each compilation step. IC context, we're going to use create and destroy for our API here, and we're just going to take in absolutely nothing for now and see where that gets us. We might want some arguments soon, but we're going to be adding things to it with other functions later. So create a IC context. I don't know what else to say. Create a liaison context. So we'll also want to, oh boy, destroy a liaison context. Just switch the order of these. Cool. So that'll give us create and destroy, and we can get files. What we'll want next is, let's say we need to put a file in there somewhere. We need a, let's do an int IC context get or add source buffer from file. I am not afraid of really long function names for things that you're not going to call very often, so we're going to let this stay long for now. Maybe we'll shorten it later. We're going to grab a context here for what we want to put it into, and we want a const car pointer for the file path that we want to load. Cool. This is going to get the source ID, get the ID associated with a source buffer. We're going to say, instead of say, get the ID of a source buffer for the given file if one has already been created. Otherwise creates the source buffer and returns the new ID. Something like that. So we could implement just about this and have everything we need for the Lexer, I think. So let's go create a new source file. In lib, new file, we're going to have context.c. So we can include liac context.h and all of our forward declarations here. We're going to need include standard lib, I believe is where malloc comes from. We're going to have to implement that in a second. We want to go ahead, though, and in our include, create a standard lib.h so that this gets overwritten. I'm going to just copy the yellow, there we go, standard lib, there we go. So then in context here, we should get an error if we try to reference malloc, because we're referencing our now empty file, or calloc for that matter. So let's say context, we're going to call it calloc. I'm going to calloc first. My LSP says it exists, but we'll see if CMake finds it. We want to allocate 1 of size of context, and then we want to return context. We'll do more initialization work later, but that's fine. Here we just want a free context, no problem. We don't need our extra docs in here. We're just implementing. Now, yeah, for our purposes, let's do a build, clean, and build. Again, I'm using my own build script. You're going to have to follow the regular old CMake stuff. This does not do what I thought it would do. Interesting. Did I set up my CMake list properly? Ah, I did not. So maybe we do a quick fix up the CMake list here. I forgot to add this as a library because, well, I didn't have any code in there. So we're going to make a new CMake lists text file. We're going to include this on the right here just so I can copy a couple things. We want to add a library, liac. I'm going to call it libac. And it's going to have some things. Let me grab something from a different project, actually. Yoink, because I want to glob some stuff. So we want to say file glob recurse. And we're going to call it libac source. And we just want I've been using project source here. Let's see if we can just star.c even, just like that. And then we can pass in our libac sources. So that gives us a library. And then we want to set our include directories here to just be project source.dir include, because that is correct. And that'll be for libac. So then up here, we can add subdirectory, and that's just going to be lib. And it's going to configure the sub project here as a library. And then we want to say target link libraries, liac lib liac, like that. And then we want to set, no, we've already got the include directory, so that's fine. I'm going to put it there. Does that work? Cool. So now we have undeclared library functions calloc and free, which we don't have in our header yet. So I can go void whatever here. We can just copy these even. If I just yoink this out of here, so this is calloc, we can come over to our standard lib, and we're going to declare calloc to be of this point, calloc of this type, rather. Void star calloc is going to take unsigned long, count, and size. Right, and then free is just going to be void. Does it return void, right? Like it has to, there's nothing to do. Free, void star, and we're just going to call it memory. So now calloc and free should both exist, and we should now be able to build this. Not that the other two things, like non-void functions returning here, but it references those files, those functions now. So we've got that. Now we need to do some additional work here, some additional bookkeeping. We need a capacity, I just realized, on our context here. So we have the sources count. Let's also do sources capacity. I'll put it here, capacity and count, because we need to know how many slots we have left in our dynamic array here. So let's do some, I was about to write an assert statement, but you know what we don't have is an assert in our standard library headers. We are going to have to handle assertions ourselves. I'm going to hold off on writing assertions and just put them in comments here then. We're going to say assert context, and honestly assert file path, probably. We probably don't need to assert file path, we can just return 0. Yeah, sure, let's just say if file path, if not file path, return 0. Easy enough, that's just invalid. There's no way to get a file from an empty file path. Then we're going to have to do some math. If we want to get a source from a source buffer, though, we can do that pretty easy. We're going to come over here then and do our assert for this. We need the context, and then we also want the context's sources count to be greater than or equal to the source ID -1, because we want the source index. Let's go ahead and just say int source index equals source ID minus 1, because we don't want 0 to be valid. So then we can just say, let me flip this around, because everybody knows how to say this, right? If source index is less than, whatever. So then we can just return context sources sub source index. And we can do one final assert here that context sources is not null. And we can actually put that all the way up here at the top. We have to have allocated some sources. Or I guess we could just say, rather, if not context sources, return the empty source. So to return an empty source, there are a couple of things we could do. I don't know which ones we want to parse first is the problem. Because we can very easily parse a YAC source buffer. We can really easily write this and just return a 0 initialized structure. I assume parsing that is going to be easy. I don't know. So we're going to handle that as we get there. So the problem here is then a source buffer just has a name and a text. So if we return an empty one, both of these are going to be null. So do we want to have a wrapper function that says, is a source buffer valid? Maybe. Or do we just want to initialize both of these to not null, to empty strings? I don't know. Both will be null terminated. They'll both be valid. So if we wanted to, we could then say name equals non-existent, unknown. I don't want to just say unknown, but sure, maybe. Text is empty. We could do that to be a bit more friendly in the API, not return null everywhere. Then, so if not context sources, or, so then this assertion should probably also not be an assertion. We should probably then say if source index is greater than or equal to this, then we do the same thing, right? So no assertions there. We just want to assert that context is not null. And then we can do that. Right, so then over here, allocating is going to be not a pain, but just, work. So we want to say if context sources. If we don't have any memory allocated yet, we're going to default it to something reasonable. So we're going to say context sources equals calloc, because I like stuff. And we want to allocate how many? Let's say a capacity of 8 to start with. Size of this thing. Right, and context sources will just be 8 size of whatever LIAC source buffer is. Let's set context capacity equal to 8, and then we can just reference sources capacity directly. And calloc takes unsigned long, and we're giving it a long. So it's going to complain if we don't cast. We know that we're fine. Unsigned long with the cast. And maybe we don't want just 8 at the start. Maybe we want something like, let's save enough space for 32. Because usually you're going to be compiling multiple source files, and we don't want it to have to spin up a bunch of small allocations at the start. Let's give it a bigger number. We have memory. And then we can, let's go ahead and just assert that sources count is 0. You don't even have to assert. You can just say context sources count equals 0. Explicitly, it should be 0 because we've 0 initialized everything up here, but just in case, we'll set it to 0. Set the capacity to 32 and initialize the sources. So then we want else, and only if the sources count context sources count is greater than or equal to the sources capacity. It should only ever hit equal to, but I like to be a little bit whatever. And this is only for allocations, I should have noted. We don't have to do this right away. We do want to look up if a file path exists first. If no file exists, if no file source buffer exists with that name, allocate space for 1 and return it. right? So then what we want to do here is expand what we're doing. The source count's not going to change just yet, but we're going to double the capacity times equals 2. Could also left shift equals 1, but we're just going to times equals 2 for clarity. Then we want to realloc all of our memory here. So we want to realloc, and we don't have a signature for realloc yet. So we want to realloc context sources. I assume just to the new capacity like that. If I go build this, is it going to tell me the realloc signature? Void, yeah, okay. So let's go back into our standard lib, grab calloc, turn it into realloc by just switching the order here. Oh, well, not really. We want void star memory. And we probably want it to be const. I don't remember if it matters. It doesn't really say, but I guess it is, potentially. I don't know. Void memory. They call it nothing, right? There's no names. So there's our reallocable, or prototype. So we double the capacity, we reallocate our storage, and now we should be good to go. So then from here, we can just set the file ID equal to source ID equals whatever the index would be plus 1. So that's the count plus 1. So then we can say sources context, sources sub, context sources count equals, we're just going to, I mean, they're already like initialized. So we could just say count name equals file path. And then text. Here we're going to need some source text that we don't have yet. We'll get that later. And then we can increment this. I'm doing it explicitly so we can see what's going on. And then we want to return source ID. So we've initialized a source with the file path as its name. And we're going to read its source text, probably in the next episode. I'm getting a little bit low on time here. So let's do this check then. We want to say for, we have long, I think is or whatever, but we'll go long, I equals 0. I is less than sources count I plus plus, which will fail immediately if sources count is 0, so we don't have to worry about it. If, now here's the next problem, we need a string compare. So let me go get the signature of stir. From doing this, we're going to compare the file path to the context sources, whatever, I, right? Context sources sub I dot name. And we want if that equals 0 to return int I. So really, we could just make this int, but then we have to convert this from long. So we'll do it this way. That's fine. We could make sources count just an int, because we are only expecting it to be an int, but I don't. We'll figure it out when we figure it out. This, other than the source text not being parsed, should be all we need to do before we start lexing, right? We've got our context that we can create. We can add source files to it. We can almost parse their, read their text in from file, and we can look them up after the fact. So with that, we can start writing a lexer, generating tokens that reference these files, these data structures, and be good to go. So thank you for watching me poke around with all this boilerplate stuff that's going to become a pain pretty soon, but we'll suffer through it. Thanks for watching episode 1, or 0. Maybe I call it 0. Of, what did I call it? Creating a compiler from scratch recreationally. Yes. And I'll see you next time.